Welcome to Module 4, the sound perception. So in this module, we will delve into how our ears and brain work together to interpret the sound. So now let's begin with the anatomy of the ear. So sound waves strike the outer ear, travel through the auditory canal, and cause vibration in the tympanic membrane. This vibration moves the ossicle, which are the malleus, the incus and the stapes, creating fluid variation in the cochlea. In the cochlea there is a liquid. The cochlea's fluid movement generates then some electrical impulses that the brain interprets as the sound. So you can see how complex is our listening process. The sound energy undergoes several transformations before being interpreted by our brain. So notably, the auricle's shape has a double function. On one side, it works like a funnel to collect the sound wave. On the other side, it helps us localize sound direction. And we will address this later on this module. But I want to run you a question. How can we listen to in 3D space, if we have just two sensors? The external acoustic mid-hus also has a double role. It transmits sound to the tympanic membrane. However, in the process, it also applies filtering to enhance intelligibility on some specific frequencies, as you can see in the picture. And those frequencies are from 2 kHz to 8 kHz. In fact, those defining the range of intelligibility. In 1933, in Bell Laboratories, they did an experiment, a very interesting experiment, that showed how our perception of sound intensity is somehow correlated to the sensation, varies with the frequencies. For example, at 1000 Hz, 1 kHz, a 30 dB sound produces a certain sensation. However, at 5/8 Hz, it takes 88 dBs in order to create the same sensation. So this finding led to the need to standardize the measurement of the sound sensation. So for this reason, we now introduce the concept of the phon, which standardizes sound sensation level based on the B value at 1000. At 1 kHz, the number of phons equals the sound pressure level, SPL, in decibels. For example, at 40 dB SPL, 1 kHz phon is perceived actually as 40 phons, so there is a relationship 1:1. The phon scale is derived from these contours, which map out sound pressure level across different frequencies that is perceived as equally loud. For example, a 40 phon sound is equally loud across all frequencies. But the required SPLs to achieve this varies by frequency. So when mixing audio, for instance, in audio production or music production, keep in mind that our ears don't perceive all frequencies equally. Our hearing sensitivity varies across frequencies. We are most sensitive around 3 kHz, where the hearing threshold is lower and the pain threshold is around 110 dB. At lower frequencies, like 300 Hz, the pain threshold increases to around 120 dBs, as is depicted in the figure. This explains why sounds in the mid-range frequencies feel more intense even at the same sound pressure level. Now a question. Do a jet engine and a piano note at the same sound pressure produce the same sensation? Well, the jet sounds louder because our perception is influenced by the sound's bandwidth. For instance, two sounds with the same pressure and center frequency can evoke different sensations if their bandwidths differ. Wider bandwidths tend to produce a stronger sensation. For the same sound pressure, the bandwidth of the spectrum affects the sound sensation produced. The duration of a sound also affects how we perceive its intensity. So short sounds like a clap seem quieter than sustained ones, even at the same pressure. So this phenomenon is why we basically emphasize certain consonants in words like apple and says. So we evolved as humankind in this way. So duration plays a key role in how we interpret sound, emphasis, and clarity. Now let's move to 3D and 3D listening. So our ability of sound location in a 3D space is a complex and fascinating process. So again, we can hear in 3D even if we have two sensors. So we locate sound sources in a space using two mechanisms. The first is the time of arrival, and the second is the head-related transfer function, HRTF. So let's talk now about the first, time of arrival. So the brain detects differences in sound arrival time between the ears, and this difference in time is basically translated into an angle of direction. Now the second, head-related transfer function, which is more complex procedure. The auricles, the pinna, or outer part of the ear, plays a vital role in sound localization by altering the sound waves before they enter the ear canal. Here is how it works. So basically the shape and folds of the auricle reflect and diffract incoming sound waves. This creates subtle changes in the sound's intensity, phase, and frequency depending basically on the direction on the sound source. The brain decodes these modifications to estimate the elevation of the sound source, whether it is above or below the listeners. Hence, sounds arriving from different directions are filtered differently due to the interference caused by the listener's head, shoulders, and auricles. The HRTF is a mathematical model that describes how sound waves are altered by the listener's body before reaching the eardrum. The HRTF is unique to each individual because it depends on their specific physical characteristics. In virtual or 3D audio system, personalized or generalized HRTF are used to recreate the sensation of sound coming from specific direction. You can listen to some examples of binaural 3D sounds available with the material at your disposal. In enclosed spaces, we perceive both direct and reflected sound, as we can see in the figure. Reflected sound takes longer to reach us, altering our perception of time and space. For instance, in a concert hall, reflected sound contributes to the richness of the experience, but also affects clarity negatively. Understanding the interplay of direct and reflected sound is crucial in acoustic design. So the Haas effect explains how our ears integrate sounds with delays under 35 milliseconds, creating a unified spatial perception. As delays increase, the spatialization effect becomes more pronounced. Beyond 35 milliseconds, we begin to perceive echoes. So we basically know what echoes is. This principle is critical in audio engineering to create immersive sound environments. So now let's conclude with some examples. First examples, let's try to calculate delay. And the formula to calculate the delay is that the reflected delay with respect to the direct path is reflected path minus direct path in terms of distance over 340 meter over second, which is the sound speed. So an example, given a reflected path which is 4 meters long and a direct path which is 2 meters long, the delay will be 6 milliseconds. Second example, let's consider the BSPL computation of reflected sound versus direct sound. So reflected level decrease with respect to the direct level since you need to have a longer path. So the reflected level at the listening position is computed using the formula 20 multiplied log of direct path over reflected path. Well, now let's apply the formula to the scenario that we have described before. So in that case, the reflected level at listening position will decrease of 6 decibel SPL. So now, reflected sound intensity diminishes with distance and surface absorption of course. Accurate calculation of this phenomenon ensure optimal sound balance in value. This principle demonstrates that the practical applications of sound perception knowledge. So let's now conclude the module. So in this module, we explored how sound perception is shaped by our anatomy and environment. By understanding these processes, we can improve audio design, create a better listening experience, and appreciate the complexity of our auditory system. So thank you for your attention.